All right, we're going to continue on with 2.5 here and finish this up here hopefully in this video. So we're going to look at some other continuous functions first. The inverse function of any continuous function is continuous on its own domain. That should be the word, domain. Okay. So remember inverse functions, the f inverse like that, okay, which is not, just so you know, it's not 1 over f of x, not reciprocal function, okay? All compositions of continuous functions are continuous, so we had that one, so don't forget that. And then also show that the following functions are continuous. Let's take a look at these. We're basically going to want to use our combinations of rules to try and figure out when they're not continuous, which we did here in the last video, these kind of properties of continuous functions things. So if we look at this one, we can actually write this as a composition of two functions. We could say that f of x is equal to 7x plus 8, and then we could say then that something like g of x, which would be the outer function, is x to the 2/7, which is the 7th root of x squared, like that. And if we look at it this way, in fact, I'm going to move this over, hold on. If we look at that, we can say then that our actual function is g of f of x, like that. That's, maybe I shouldn't have used f. Hold on, let me change this to h of x, and I'll make this an h of x as well. That way I'm not, and that equals our f of x function. There, that's better. That looks like our original function. And if we look at this, it's a composition of functions, and so this one is continuous from negative infinity to positive infinity. It's continuous everywhere. And the one below it is also continuous, from negative infinity to positive infinity. And so if those two are continuous everywhere, then the composition of them is continuous. So each individual function is continuous. This is just a polynomial. And the other is just 2 an odd power. Those were continuous, right? Remember back here with powers and also polynomials being continuous. So we have 2 continuous functions there, and then the composition of them that we were just talking about. All compositions of functions are continuous, and there is an actual theorem for that, and it is the composite of continuous functions. So composite of continuous functions, and this is a theorem. And basically what we're saying is if function f is continuous at c, and g, the function g is continuous at c, then the composite g of f, or f of g, is continuous at c. So composite functions of continuous function are continuous, and this is what we have here, a composite function of continuous functions. After this, we have a couple more. I'd like you to go ahead and give a try to use those rules and see if you can show that these are continuous functions. And then next, let's take a look at finding limits. Sorry, I was scribbling some stuff there before I was looking through this ahead of time. So find the following limits. So what we're going to say here is that if, it's another theorem, limits of continuous functions, if g is continuous at the point b and the limit as x goes to c of f of x equals b, then the limit of the composite g of f of x equals g of the limit of the inner function, basically. So what that means is if we look at something like this, you could go through and you could try plugging in the x over 2 and doing all of this stuff. But what we're saying is we have a composite of functions here. We have something like, we have g of x equaling just cosine of x, and f of x equaling 2x plus sine of 3 pi over 2 plus x. Okay, and so this is a composite function, which means since it's a composite function and it's continuous at the point b, which is what the limit of the intersect is, we can simply rewrite this to be equal to the limit as, oops, I don't want that first, sorry, hold on. We want this to have the limit on the inside. We can rewrite this in this manner right here, right? We're starting with this over here, and we can rewrite it in this form, where we're going to get cosine of the limit of what's on the inside. And so you could do this out the long way, or you could just do this. 2x, so it's kind of a little bit, can be a little bit of a shortcut for you, or help you maybe make take a limit of something a little simpler. So something like that. Okay, we can make it into that. And so we can take the limit of what's on the inside, so this becomes the cosine of, and here we can just go ahead and plug in the pi over 2 everywhere, and we'll get 2 times pi over 2, because it's not going to give us anything that breaks our function, so then we can do plus the sine of 3 pi over 2 plus pi over 2. Okay? And so then we've got the cosine of 2 times pi over 2, which is just pi, plus the sine of 3 pi over 2 plus pi over 2 is 4 pi over 2, which is 2 pi. So it's the sine of 2 pi. And the sine of 2 pi is 0. Okay? And so we end up just with the cosine of pi, which is negative 1. And you should know this from your unit circle. If you look at your unit circle, if we go around 2 pi, that's going all the way around once. This is 2 pi, and the coordinate there is 1, 0, which means the sign is 0 because the sign is the y value. We're not at all any distance up on the y-axis. Right, there's our x-axis. And then if we go to pi, that's just going around to here once. So there's pi, and that's the point negative 1, 0. And since we're looking at cosine, it's the x value, which means we want that value right there. It's negative 1. So just from the unit circle, there you go. We end up with that. If you went through and did the whole thing out the long way and just actually started plugging in the pi over 2 right here in this version of it, you should get the same answer, but this might help you do it a little easier. So this one, I'm going to leave these for you to try, and I'll write these out in the notes for you to take a look at, and you can see if you got them right. They're not too hard. I think the first one, maybe 4 lines, 4 pretty simple lines with a lot of detail, but the thing you should try to do is get rid of that discontinuity as you take the limit. Don't forget to do that. So in other words, factor that denominator. It has the difference of 2 squares. And then for the other one, should be even easier. You give that one a try and see how it turns out for you, okay? All right, next we've got what is called an intermediate value theorem for continuous functions. Basically, the idea is saying that if you have a smooth continuous function, it's continuous on some closed interval here between a and b, that it will cross every single possible value or output value, right? So our output values will range from f of a to f of b, that it'll cross every single output for in between them, that you'll cross every single possible output between them. So any horizontal line you draw between them will cross the graph at some point. And if you want to try this, take and draw a curve like what you see right here. Okay, so if you draw that curve, and then the challenge is to put your pencil down right there at the beginning. So this will be the start. Then up here, this will be the end. And what I want you to do is draw a horizontal line entirely anywhere between them across your paper like that, some horizontal line all the way across the paper. And then what I want you to do is put your pencil down at start, and without ever lifting your pencil off the paper, I want you to draw a line all the way to the end point, right? So from the start to the end point, draw a line. It doesn't have to be along the curve. Just draw any line you want between those 2 points without crossing the horizontal line that you draw. So like if I was starting here, no matter where I try to, even if it's not a function, I'm going to have to cross that line at some point, right? Like every one I draw, everything I try to do to connect these two, if I actually end up connecting them, I'm crossing that horizontal line. And it could be any horizontal line anywhere in between them. Any horizontal line you draw in between them will cross the lines that you are drawing. Okay, so try that challenge and you'll see you can't do it. It can't be done. And so therefore, that's what this is basically saying. It's basically saying that if you have a smooth continuous function, every single value between the start and the end will be obtained. It's my understanding this was actually used at one point to give tickets, speeding tickets, to people who I can't remember where, but it was a toll road where they'd get on the toll and they'd be given a ticket that said when they got on the toll. And then when they got off, wherever they got off, it would also note the time that they got off. And the idea was that say that the speed limit was 50 miles per hour and you were going 100 miles, it should take you 2 hours. So if you ended up showing up in, traveling that 100 miles in under 2 hours, that meant you had to have sped. You had to have gone above the speed limit. So say you went 100 miles, but you did it in only an hour, right? That meant that you had to have been speeding, right, at some point. Now, what they would then do is immediately pull you over and give you a ticket in that situation for having gone 100 miles per hour. And their argument was, you may not have gone 100 miles an hour the whole time. You might have gone 150 for part of it and 25 for part of it and all that kind of stuff. But because of this intermediate value theorem, they're saying that if your average speed was 100, then that means that at some point you had to have obtained that average speed, because you had to have either gone above it or below it. If all your speeds are under 100, you can't average 100. Just like your grades. If all your grades are under 100, you can't average 100. So if you average 100, that meant you had to have been either going it the entire time or at some point been above it or below it. So that means you had to have gone that speed at some point, and therefore they would give you a ticket. So anyway, just a little interesting there. Aside there. So geometrically, the intermediate value theorem says that any horizontal line y equals y naught crossing the y-axis between the numbers f of a and f of b will cross the curve y equals f of x. That's what I was saying. Draw any horizontal line, and you cannot draw it without crossing that function, and it will cross it over the interval ab. I don't know why that space is there. If f is discontinuous at even 1 point, all right, at even 1 point on the interval, the theorem's conclusion may fail. May fail. All right, so take a look here. Consider the function f of x equals 2x minus 2 when x is between 1 and 2, and equals to 3 when x is between 2 and 4. You can see it pictured over here. Okay, so consider this function. It has a discontinuity. It's discontinuous at x equals 2. And so the question is something like, what value of c will give you an output of 2.5? All right, so what value for c will give you 2.5? Now note, here is the line, here's 2.5. And so we want to know, what do we plug in for x that'll give us that 2.5? And the answer is nothing. There is no c to give 2.5. And so then see, that makes the previous statement, the intermediate value theorem, break, because we have a break in the graph, and we can draw a horizontal line that is there. So there's no c to give 2.5 because it's discontinuous. It's discontinuous. And now remember, it said may fail. What if instead they asked the question, what value of f of c will give you an output of 1. And the answer would be C equals 1.5. Okay? So our output would be 1. This is what we're looking for. And then if you look, if we just put in 1.5 right there, that takes us up to 1, and that gives you the value of 1.5. So it's, again, it's that may fail right in here. It may fail. And remember, we're only looking in here, so we don't have to worry about whether or not it hits that value, outside of it or anything like that. This is where we are limited in our domain. Okay. Intermediate value theorem also helps us find the existence of a root or zero of a function. And this will actually help you, you can narrow it down. So show that there is a root of the equation x cubed minus x minus 1 equals 0 between 1 and 2. So we have a continuous function. We have no breaks. Then this will work. So what we can say is, if we look at f of 1, we're going to get 1 cubed minus 1 minus 1, and that's going to equal negative 1. Okay? And then we can look at f of 2. F of 2 is 2 cubed minus 2 minus 1, which is ultimately going to equal 5, because this is 8 minus 2 minus 1. So this is going to equal 5. And so if we look at this function, just a quick little sketch of it here, what we'd find, this is f of x, is we have to go from negative 1 at 1, so this point, and then 1, 2, 3, 4, 5 at 2. So we're at the point 2, 5 here, and the point 1, negative 1 here. And so again, a root basically just means, right? You've got to remember, a root means that f of x equals 0. Okay, that's this part right up here. A root is also known as a solution. F of x equals 0. And so the idea is, do we ever cross this horizontal line between them? And the answer is yes. Basically, because one of the results is negative and one of the results is positive, any line I try to draw in between here will cross the x equals 0 line, and therefore there is a root. And so if you're having trouble figuring this out, you could say, all right, there has to be a root between negative 1 and 5. And then so you could make, or I'm sorry, negative 1, there has to be a root between 1 and 2. I'm looking, all right, between 1 and 2. Well, if you wanted to narrow it down, you could then try maybe between seeing if there's a root between 1.5 and 2. And if, say, 1.5 turns out to be negative and 2 is positive, then you say, yes, there's a root between them. But if 1.5, I'm not doing it, so this is just hypothetical. You can try it if you want. But if 1.5 turns out to be positive, and you already know 2 is positive, then you know that the root is not between 1.5 and 2, that the root must be between 1 and 1.5. So that would tell you that this would be negative, this would be positive, and so the root would be between these two at that point. And then you could go and you could try 1.25, let's say. And you could say, oh, look, 1.25 turns out it's positive as well. So then the root is between 1 and 1.25. And you see, you could keep having it, cutting in half, and keep working back and forth to try and come up with a narrowing down of what the root is. Okay, and you could even get it down to like some decimal places by just kind of jumping back and forth, and it would go pretty quickly for you if you did that. Next, continuous extension to a point. Consider the function y equals sine of x over x. Here, its domain is negative infinity on up to 0, but not including 0, because 0 makes the denominator 0, which would make it undefined, and then 0 up to infinity. We can do that as our domain. Here's the actual graph of it there to the right. There's your function. And so this function is continuous at every point except x equals 0. This is a removable discontinuity, and I'm going to show you why it's removable. So we can extend the function's domain to include the point 0, 1, because right now it doesn't, in such a way that the function is continuous then at x equals 0. And we do this by defining a new function that's similar, but basically it's kind of like it's piecewise. So we're going to say f of x equals and we're going to make this equal to f of x, right? Whenever x does not equal 0, so it's the regular sine of x over x. And then we need to put something else here, some other function here for when x equals 0. And we can do that by simply saying we're going to make this sine of x over x whenever x does not equal 0. That's our original function. And then we can just say, well, what is the actual limit of that function? You know, what is the limit as x goes to 0 of f of x? What is that limit? Which is the limit as x goes to 0 of sine of x over x. And that limit is 1. Look, as you go from the left, you get to 1. As you go from the right, you're headed towards 1. And so it's 1. So we just want to put the value of 1 there, all right, when x equals 0. Okay? And then that function right there is defined everywhere, and now it's continuous. So let's take a look at this one. Here, I'm going to start you off on this, and I'm going to let you finish it. Basically, you want to do this again. It's got a discontinuity, right, at x equals 2. And so what we want is we want to look at a new function here where we use the old function, f of x. That's this right up here, okay? And then we need a new function here for its value at that point, and it's just going to be the limit as x goes to 2 of f of x, okay? And this one will be at x not equal to 2, and this one will be at x equal to 2. Okay, so see if you can finish this off, write what f of x is, and again, I'll write it down in the notes for you to have. Okay, this one, last thing for this section, I believe, yep. So here, what we want to do is find a value for a that will make this a continuous function. So if we look at the first part, it's x squared minus 1. If we actually graph that, oops, it's almost time for class here. So if we actually graph this, okay, x squared minus 1 is a parabola right here. It's like this, okay? And so for x less than 3, this is just going to go on out forever over here. But over here, it's 1, 2, I didn't do that very well. 1, 2, 3. So this is just going to kind of continue up. Boy, I really didn't do that very well. Let me redraw this part right here. So let's make this 1, 2, 3, and we're going to come kind of this way and go up like this. And so here is where we are. And then that one's going to stop right there. Notice it's not or equal to, so it'd be kind of an open circle. So that's just this top part right there. What we want to find is we essentially want to make some sort of line. This 2ax, that's just a straight line that goes through the origin. And so what we want to do, I'm going to use a color like yellow here, is we know that we can have any number of straight lines that go through the origin, like that one. Let me turn on the straight line tool here. So let's go, we could have this one, or this one, or this one. I started missing the origin on that, or, you know, this one, and this one up here, and this one up here, and pretending all my lines are actually going through the origin right there. I didn't do a great job on some of them, like that one. But let's get it through the origin, okay? Well, there's going to be one in particular that's going to go through the origin and also through that point. That was really bad. Let's try that again. It's going to go through the origin and through that point. So pretend that actually goes through the origin. That's the line we want to find, and then that's going to be our function that we're going to use for this part of the graph starting right there. Okay, let me draw that in. Okay, that's where we're going to use it. And so we can do this by finding when does the limit as x goes to 3 minus, so of x squared minus 1, we need to set that equal to 2a at x equals 3. So we're looking at x equals 3 here, right? And so what we want is we want 2a of 3. We want this point right there on the red function, right? On this function right here. We want that to equal what x squared minus 1 was going towards, okay? So we have the limit of x squared minus 1 equaling what the value is there. So we're going to try and figure out what value of a will make that true. So the limit As x goes to 3 from the left of x squared minus 1, we can just plug in 3 there because it doesn't give us any issues. So this becomes 9 minus 1. So this is an 8. Over here on this side, this just becomes 2 times 3. It becomes 6a. And then we end up with 6a equals 8, which means a equals 8 over 6, which is just 4/3. And so that's our answer. A equals 4/3. If we plug that in, then it will be continuous, and then the values will be the same at that point. In other words, they're going to equal at that point. Okay? So that's pretty much it for this section. Be sure to look back at the ones I said I had for you, the notes, to see them after you try them yourselves. Okay, thanks a lot.